Open Shortest Path First, or OSPF, is probably one of the most complex routing protocols in use in networks today. Now, before I continue and explain a little bit more about the OSPF, let me clarify one thing first. And this is this word open at the beginning of the name of OSPF. This word open doesn't reflect the action of opening something, opening this shortest path first. It rather implies that this is an open implementation of the shortest path first algorithm. And open shortest path first algorithm, or Dijkstra algorithm as it is sometimes known, is the foundation of all link state routing protocols. So OSPF is one of the link state routing protocols. Another very popular routing protocol used in networks today that is also link state routing protocol is ISIS, or intermediate system to intermediate system. But I digress. So in this module we are going to talk about what is the link state routing protocol, what makes up the link state routing protocol. We are going to talk briefly about the neighbor adjacencies, the information exchange in OSPF, the link state database where the information about OSPF routes, so to speak, is kept. Then we are going to talk about the different areas, external routing, and finally about summarization and filtering in OSPF. OSPF is, as I said, an open implementation of the SPF protocol, and it has been defined in the RFC 2328. This RFC has been written, if I'm not much mistaken, in 1998, but it is still valid and in use today. Link state routing means that the routers, all the routers that participate in the network, have the full network visibility. And by full network visibility, I mean that there is a database that contains the information about all the links in the network. And links are simply interfaces, and information that is kept about these interfaces are their metrics and the relationships with other devices on those links. In other words, on these in this database, we're going to have information not only about the interfaces themselves, what are the IP addresses and the networks associated with them, but also what other devices are connected on these links. Now, when we have this information in the database, and which is fundamental for the functioning of the OSPF, the SPF algorithm runs. SPF algorithm, or Dijkstra algorithm, is a mathematical algorithm from the theory of graphs, which is simply designed to find the shortest path that satisfies certain conditions. In our case, the shortest metric, the smallest metric between two nodes in the graph without going through the same node twice. In other words, it is going to calculate a loop-free path through our network based on the information in the database. In order to build the database, in order to exchange the information, OSPF first needs to form neighbor adjacencies. Neighbor adjacencies consist of several processes that happen in sequence. The first is the discovery of the neighbors, how the neighbors find out about each other, what are the processes involved there. And this is where OSPF uses something that we call the hello protocol, just like EIGRP, but it's a little bit more advanced than the EIGRP's implementation of the hello protocol. Also, how these adjacencies are maintained, how the routers detect if the other neighbors are no longer available on the links, and so on. And also there are some optimizations in this neighbor maintenance and discovery process. Finally, we have the information exchange. How do OSPF routers exchange the information about what they have in their databases? And this is where we are going to talk in detail about the link state advertisements, the data structures that OSPF keeps in the database that are used to calculate the best paths and communicate the contents of the database and the local interfaces. Also, in some cases we want to limit the scope of the SPF calculations. We want to carve out our network into smaller, more manageable pieces, and this is where OSPF areas come into play. And when we are talking about the operations between these areas, this is where we talk about the inter-area operations, OSPF is no longer really a shortest path first protocol. It's no longer a link state protocol. It resorts to really something that is very, very similar to the distance vector behavior. OSPF in RFC 2328 doesn't call this distance vector, they call it the partial SPF, but it's really just a distance vector behavior. But as the slide says, don't tell anyone that. And at the end, we are going to talk about summarization and filtering in OSPF. And as we will see, summarization and filtering, unlike other protocols, may not always be possible in the OSPF for various reasons. You can summarize and you can filter the routes, but not anywhere in the network. You have to do it at predefined boundary points in our network. When we talk about OSPF routers, there is a special identifier that identifies each router in the OSPF network uniquely. This identifier is a 32-bit number that is called the router identifier, or short as router ID. Router ID looks and feels like an IP address, but it's important to understand that the router ID is not an IP address. By default, OSPF routers are going to select the router ID from one of the IP addresses from one of the interfaces, and the preference here will be given to loopbacks. If there are no loopbacks, any interface becomes valid as the router ID. Any interface's IP address becomes eligible to become a router ID, and then within the category of the interfaces, so if we have multiple loopbacks, one with the highest IP address will be the one that is going to lend its IP address to the router ID. But once this number has been chosen and inserted into the OSPF as the router ID, we need to stop thinking of it as an IP address. I know this may sound confusing, but I will show you this in more detail later on when we start looking into how OSPF actually works in Cisco IOS. Also, not all routers in our OSPF network are the same. Some routers have specific roles. The primary role, or the role that is given to just about every router in our OSPF, is simply an area router. Area router is the router that has all interfaces that are in a single area. This router is going to be exchanging information with other routers in that area, and it's going to be forwarding the traffic. So this is the most simple, the most basic of all roles that the router can perform in OSPF network. And really, all routers are area routers. A special case of area routers are routers that are in a special area which is called the backbone area. And I'm going to talk about the areas in just a minute and different area types. Routers that are sitting on boundaries of multiple areas are something that we call area border routers, or ABRs for short. In Cisco's implementation of OSPF, area border router, or the ABR, is defined as the router that is connected to area 0, or the backbone area, and one or more other areas. Not all vendor implementations of OSPF have this definition of the ABR, and RFC is a little bit unclear on that definition. There is actually a separate RFC, I cannot remember the number right now, that is written about different vendor implementations of what makes ABR and ABR. But in the Cisco world, ABR is the router that sits between the backbone area and one or more other areas. Another special role for the routers that we have in our network are autonomous system boundary routers, or the ASBRs for short. ASBRs are those routers that are injecting external information, external routing information into the OSPF domain. And external routing information simply means that this is the router that redistributes some information into our OSPF domain, that injects external routes. Not only that OSPF makes the difference between different router roles, not all interfaces in OSPF are the same or behave in the same manner. And this is where I'm going to talk about the network types, or you should think about the different interface types that OSPF recognizes. OSPF recognizes point-to-point network type, broadcast network type, non-broadcast network type, point-to-multipoint, point-to-multipoint non-broadcast. There is one more that is very special case, which is loopback. Loopback interfaces are special in OSPF, and this is again something that I will show you in a little bit more detail later on. Now, for these network types here, one thing that I should maybe mention here is that point-to-point is the default on all serial interfaces on, for example, GRE tunnels, and if you are using frame relay, on point-to-point frame relay sub-interfaces. Broadcast network type will be default on all Ethernet interfaces. Non-broadcast is going to be the default on all frame relay physical interfaces or frame relay multipoint sub-interfaces in a case that you have to deal with frame relay, which I find very unlikely. Point-to-multipoint and point-to-multipoint non-broadcast are not default on any of the interface types, but they can be specially configured. They have a particular behavior that might be of use for you in the network. And finally, I did mention that there is a last one, which is loopback, or loop as iOS calls it, which is going to be the default on loopback interfaces. And there is a special behavior about the loop interface, and as I said, I will talk about it in a little bit more detail later on. In order to exchange information, OSPF uses different packet types. Now, these packet types are always sent on the local link on the network as IP protocol 89 packets. So OSPF doesn't use TCP or doesn't use UDP. It has a specific protocol type 89 that is reserved for its use. These packets can be either sent as unicast packets to a unicast destination, or they can be sent as multicast packets. And in that case, what we are going to see are link local multicast destination addresses of 224.0.0.5 or 224.0.0.6 in some special cases. OSPF has 5 different packet types. There is hello, the database descriptors that are used to exchange information about the contents of the database, not the actual contents of the database, but information about what's in the database. Think about it sort of as a table of contents or menu of the OSPF database. And then there are 3 packet types that are going to be used for the actual exchange of the information, for loading the database from one neighbor to another, and these are link state request, link state update, and link state acknowledgement packets. They're either called LSA request, LSA update, LSA acknowledgement, or short for LSA rec, LSA upt, and LSA ack there. And these 3 packet types here are going to be used in a very interesting way. When we have 2 neighbors that have to exchange the information, the neighbor is first going to send out the request, then another neighbor is going to respond with an update, and then this neighbor that receives it needs to acknowledge that it actually received this information, because these 2 neighbors need to be sure that this information is exchanged. And again, this is something that we are going to go in greater detail a little bit later on. For now, we are just going briefly over what OSPF and how it works. And finally, the information that is being exchanged here, the contents of the database, are link state advertisements, the LSAs. And in OSPF, there are different types of link state advertisements, different bits of information, different, I should say, database entries, different kinds of database entries that carry different sort of information. And these are the most common ones. There are some other ones. I'm going to briefly mention them later on. But these are the ones that you really need to understand. There is type 1, which is called the router LSA, and every single router in the network is going to be generating this LSA. And basically, the major content of this LSA are the router links. These are the database contents. These are the database entries that carry the information about all the links, all the interfaces on the router that have been enabled for OSPF. And here we are going to have the information about the IP addressing, we are going to have the information about the metrics, and we are going to have information about neighbors that we might have on this link. Type 2, or the network LSA, is a special LSA type that is generated by the routers that are called designated routers, and I'm going to talk about them later on. This has something to do with the optimization of the neighbor adjacencies on multi-point segments, like for example Ethernet, where we could have multiple neighbors, not only two neighbors. Type 3 is the inter-area reachability information, which is basically the summarized routing information when it's transferred between the areas, and these LSAs are generated by area border routers when they inject routing information between the areas. Type 5 and Type 4 LSAs are used to carry the information about the external routes. The Type 5 LSAs actually have the information about the external routes that have been redistributed into OSPF, and Type 4 carry the information about the ASBRs that have redistributed these routes. And I will explain this in greater detail later on. And I have to tell you one thing, that Type 4 LSA is probably the most confusing LSA type for students who are not very experienced with OSPF. But don't be stressed, I will explain it in great detail. And Type 7 is very similar to Type 5, but in a special area type that is called the NSSA area, or the not so stubby area. And speaking of areas, let's talk about them a little bit. I did mention that there are different areas in OSPF, and not all areas are the same. OSPF relies on a hierarchical design of areas. There is one area that is considered to be the backbone area. This area has the area identifier of 0.0.0.0, or simply area 0. This is how it can be represented in iOS, but technically speaking it's also a 32-bit number, just like the router IDs are 32-bit numbers, but area 0 is a special case and it can be represented as just 0. There are other areas that can have any identifier, also a 32-bit number, and in iOS they can also be represented as a single number. Like for example, instead of calling area 1, we can call it area 0.0.0.1 because it is a 32-bit identifier that is or can be represented in a dotted decimal format, just like an IP address, but remember, it's not an IP address. All areas must connect to the backbone area. That means that if I have, for example, some routers that are in area 1 and some routers that are in area 2, I cannot connect these areas directly with the router. This is not a legitimate configuration in OSPF. What I would need to do is I would need to connect area 1 to some area 0 here, and then I would have area 2 here, and I would have to have the routers that sit between them like this. Now, this could also be, for example, a single router. I could have area 1 here, I could have area 2 here, and I would have area 0 here, and I could have a single router that has connections in areas 1, 2, and 3, but this still means that area 1 is connected to area 0 and area 2 is connected to area 0. Technically speaking, or I should say logically speaking, there is no connectivity between areas 1 and 2, even though we have a single router that is interconnecting them. So there is this hierarchical design, and I will explain this in great detail when we look into how the routing information is exchanged between different areas. We are going to see that all information must actually flow through area 0. Information, not necessarily the traffic. Keep that in mind. It is also important to understand that in OSPF, routers themselves are not members of any areas. It is the interfaces on the routers. So we could have a router that has multiple interfaces, and all these interfaces are in different areas. As long as one of them is area 0, then it's a legitimate setup. In this case, this router here is member of 4 areas. Let's say area 0, area 1, area 2, and area 3. This is perfectly fine. And this router will have a separate database in area 1, separate database in area 0, separate database in area 3, and a separate database in area 2. And this router here will be an ABR. ABR is the router that sits between the areas, and it has two major functions. One function is to provide reachability information between those areas, and the second function is that this represents the filtering point. This is the place where we can actually perform route filtering. Inside the area, we are very, very limited at what information and where we can filter. I'll explain that in greater detail later. But between the areas, we can filter the routes any way we like. So this is a filtering point. And speaking of different areas, not only that all areas need to be organized in a hierarchical fashion, that they all need to connect to area 0, but not all areas behave the same way. There are different area types. There are normal areas, and backbone area is an example of a normal area. There are also stub and total stub areas, and the difference between these areas is in which LSAs are allowed to exist in which areas. For example, for normal areas, we can have LSA types 1, 2, 3, 4, 5, but we don't have LSA type 7. This is specific for the NSSA area. In the stub areas, for example, we can have type 1 LSA, we can have type 2, we can have type 3, but we cannot have types 4, 5, and 7. In a total stub area, we can have types 1, type 2, and we can have type 3, but it's only going to be the default route that is going to be injected with type 3 summary, and we cannot have types 4, 5, and 7. In the case of the NSSA area, we can have type 1, type 2, type 3, but we cannot have types 4 and 5, but we can have type 7. Similarly to this, totally stubby, not so stubby area can have types 1, 2, 7, it cannot have 4 and 5, and it will have the default route as type 3 summary, but all other routes that might be coming from different areas are not going to be there. So there are these different area types that exist that allow us to provide some sort of built-in architectural filtering of what kind of routes we want to have in different parts of our network. And finally, there are external routes in OSPF. External routes are routes that have been redistributed into OSPF at the redistribution point, which in OSPF is called Autonomous System Boundary Router, or the ASBR. And this is yet another summarization and filtering point. At the ASBR, we can summarize the external routes as they are being injected, or we can filter them before we inject them into the routing domain. But once we have injected them into the routing domain, we can no longer summarize or filter them anywhere, unless we are dealing with different area types that are not allowing any of these LSAs to go through. And external routes in OSPF are carried in normal and backbone areas using type 5 LSAs with a little bit of assistance from type 4 LSAs, and in the NSSA and not so stubby NSSA areas, in totally stubby NSSA areas, these external routes are carried in type 7 LSAs. Not only does the OSPF differentiate between different link state advertisements, but when the routes are injected into the routing table by OSPF, they are differentiated based on where this information was learned from. And there are 3 types of routes in OSPF. They are internal routes. These are the routes that are calculated from the type 1 and type 2 LSAs, and these are the most preferred routes by OSPF. The second preference is given to inter-area routes. Inter-area routes are carried by type 3 LSAs, and they are, generally speaking, the result of one ABR calculating routes based on type 1 and type 2 LSAs in one area, and then summarizing and sending this information into another area. The last preference is given to the external routes, and these are carried by type 5 or type 7 LSAs. In the external routes, there are actually 2 subtypes even of these 2 routes, depending on what kind of metric type they carry. There is metric type 1 and metric type 2. And the difference between metric type 1 and type 2 is how the final metric for these routes is going to be calculated. For type 2 metric, the external cost is preferred over the internal cost. Even though internal cost is not entirely disregarded in this case, it is preferred over the internal cost. And with type 1 metric, the internal and the external cost are treated the same. External cost in this context, and in this context here, is the cost to reach the external prefix from the ASBR that has redistributed this route. The internal cost is the cost from the router that is calculating the path to reach the ABR. So in a case of type 2 routes, of type 2 metrics for the external routes, we are going to give a little bit more preference to the routes that are cheaper on the outside, but we don't care how much it costs us to actually reach the ABR. But for type 1 metrics, we actually do care what is our cost to reach the ABR. So again, OSPF gives you the capability to give preference to one or the other type of calculation depending on what you are trying to do in your network. And speaking of filtering in OSPF, internal routes, that means the routes that are carried by type 1 and type 2 LSAs, can only be filtered inside an area locally on the router. That means that if the router has information in its link state database, we cannot prevent that router from selectively communicating this information to some neighbors. In other words, we cannot filter the information between the neighbors. If I have it in the database, I have to let my neighbors know about the information in the database. But what I can do is I can selectively and locally, when I'm calculating my own routes, I can decide that I do not want to use some information. And this is what I mean by locally filtering between the database and the routing table. We can use filtering between the database and the routing table, and we can tell the router, do not use this information from the database when calculating the local routing table. But you know what? Even if we filtered it locally, we would still have to inform our neighbor that we do have this routing information available. When it comes to the inter-area routes, they can be filtered at the ABR, at the area border router, and they can also be filtered depending on the area type. Some area types, remember stub areas, they simply do not allow type 3 LSAs to go in there, except for the default route. The external routes can be filtered at the ASBR or at the area type boundary. And the area type that does not allow external routes to be injected from the backbone into that area is the NSSA area. So type 5 LSAs cannot go back, or not back, they cannot go into the NSSA area. So this was a very, very brief and very quick overview of OSPF, so let's now dive into more details.